Welcome to qnawire.
So the first thing that they're asking us is the speed of the hurricane near the rim of the velocity of the hurricane near the rim. So we can say that angular momentum is conserved. So angular momentum defined by the moments of inertia times omega r. This denotes rim is going to be the moment of inertia of the eye times the omega of the rim. And we're simply going to substitute in for these formulas of the radius of the rim, and then omega, the angular velocity of the rim would be the velocity of the rim divided by the radius of the rim, and this is going to equal, again, 1 over 2 the radius of the eye squared. This is also squared. And then the velocity of the eye divided by the radius of the eye for the angular velocity of the eye. So here we can simply cancel these halves out, cancel these m's out, and then we're going to be simply left with the radius of the rim times the velocity of the rim equals the radius of the eye times the velocity of the eye. Thankfully, this cancels out with this squared, and this squared cancels out with this. So once we have this, it's quite easy. So we can say that if we want to find v of r, which we're trying to find, we can simply isolate it. The velocity at the rim is going to be equal to the radius of the eye times the velocity of the eye divided by the radius of the rim. And this is going to be, the radius of the eye is 30 meters, and then we have 200 kilometers per hour. And then we're going to divide this by 350 kilometers per hour. This is going to give us 17.14 kilometers per hour. Now, this is not in meters per second, and it would be greatly beneficial to have it in meters per second. So using any conversion, you can use a calculator, or you can do this by simple dimensional analysis. But these are actually equal to 4.76 meters per second, and then 200 kilometers per hour is going to be 55.556 meters per second. And once we have that, these are the values that we're going to be using from now on. This would be the velocity of the rim, and then this would be the velocity of the eye. And then at this point, we can say that part B is asking us, what is the temperature difference? So the temperature difference is going to be based on Bernoulli's equation. So P plus the density times the acceleration due to gravity times the height plus half of the density times the velocity squared equals some constant. And if we were to compare this side of the equation from the rim of the hurricane to the eye of the hurricane, the only thing that's actually different is the velocity. Because, of course, the density of the air isn't going to change. Rather, we assume it's not going to change. And then the gravity is, of course, not going to change. The height of this hurricane is not going to change, given that it's on the same plane. And so essentially, we can say that the change in pressure from the eye and the rim is going to be simply half times the density of the air. And then we're going to have the change in velocity squared. At this point, we can actually substitute again. So half the the density of the air here will be 1.2 kilograms per cubic meter. And then for the difference in velocity, the difference in squared of the velocities, we would be using these over here, these meters per second. So it'd be 4.76 squared minus 55.556 squared. And once we find this, we can see that there's a negative change of 1,838.29 pascals. Now it's asking us, so this is going to be, if this was the answer for part A, this is the answer for part B. And part C is asking us rim or eye, which has the greatest pressure. And according to Bernoulli's equation, the rim is going to have the greatest pressure, because at the eye, a lot of the, in terms of Bernoulli's equation, because this entire term right here is equal to a constant, we want this P to be maximized. So we're looking for where the P is going to be max, which has the greatest P. So in this sense, if at the eye, a lot of the energy is coming from the velocity and not the pressure. However, at the rim, a lot of the energy of this hurricane is actually from the pressure of the rim, because at the rim, there really isn't that much velocity. There isn't really that much velocity to begin with relative to the eye. I mean, the eye is at 55.556 meters per second, and the rim is only 4.76 meters per second. So if we're asking if all of this, if this term is constant, that means that the rim has to have the greatest P. So which has the greatest P? The rim. And this is and then again, this is simply because if the Bernoulli's equation, the sum of the Bernoulli's equation is a constant, most of this constant here is going to be coming from the P, given that the rim does not have a high velocity. And then D is asking us if at the eye, all of the kinetic energy could somehow transfer into gravitational potential energy, how high could this hurricane be, or how high could this air travel? So if we were to say that all of the kinetic energy is going to be converted into potential energy, we could say that half mv squared equals mgh. And then we're going to cancel these m's out, and that h is going to be equal to v squared over 2g. We're going to use the 55.556 meters per second here again. So 55.556 meters per second squared divided by 2 times 9.8 meters per second squared. Solving for this, we find that the height is going to be equal to 157.47 meters. So if all the kinetic energy at the eye were to somehow be converted into gravitational potential energy, it could reach a height of 157 meters. And that's the end of the solution. Thank you for watching.